Hello there, everyone, and welcome to this weekly presentation of Morrison Planetarium's Tour of the Universe, coming to you live and direct from the California Academy of Sciences in San Francisco, California. I'm Bing Kwok, Assistant Director of Morrison Planetarium. Thank you very much for tuning in and joining us from wherever you are. We hope you're well, and we'd appreciate it if you drop your location in the comments. We'd love to know how far out we're reaching and where you're watching from. Usually we have viewers from the UK and India and other parts of the world. We'd love to know who's hearing us today. As always, if you have any questions or comments, please feel free to drop them in the comments and we'll try to respond. Or maybe my producer, Hayden, will drop a link or two to give you some leads as to where you might be able to find some answers. And our vehicle for this trip through the universe, the visible universe, is the astronomy visualization program OpenSpace, which is supported by NASA and which is available as a free download from openspaceproject.com. Now, if you like what you see on your screen, you can install this very same program on your computer at home and fly through the universe. The download link will list the hardware requirements for optimum performance. And again, openspaceproject.com. We also have a link to a survey where you can tell us what you think of the software, and the developers can use that feedback to improve the program. OpenSpaceProject.com. Now, the survey still has 2022 in the title, so that's the one we're still using, but that'll be updated soon, we hope. Now, with that, let's take off on a trip to outer space, and we're going to start our trip about 250 miles above the ground, or 400 kilometers above the surface of the Earth, which is 4 times higher than the official boundary of outer space. Now, why is that the official boundary? 100 kilometers. Well, a number of years ago, someone calculated the altitude at which the atmosphere is so thin that air control surfaces like wings, flaps, and rudders don't work. So way up here, above 100 kilometers or above roughly 62 miles, you need rockets to maneuver. And so 4 times higher than that, an object is in a more stable orbit, things like the International Space Station, which we're looking at right now. And this is our current home away from home. This is as far as humans travel from the Earth, at least for a little while longer. Hopefully, they'll be going a lot farther than that soon. The International Space Station was constructed beginning in 1998. It has been permanently occupied, continuously occupied rather, by crews of astronauts since about the year 2000. And right now there's a crew of 7 space travelers on board, representing the different countries that got together to build the International Space Station. This is the largest thing in Earth orbit, largest thing ever built in space. It's about the size of an American football field. And it's so big that when it's seen from the ground, it looks like a bright star. You can even get some predictions as to where the space station can be seen from any location on Earth. And there are several places where you can do it. NASA has one link. There are a couple of other really good ones where you can get good predictions as to whether or not the space station will be visible from your location. So try to find those and see if you can spot the station in the sky. As we leave the space station, we're now traveling even farther out than humans have ever traveled, and we're gradually leaving the Earth behind. You can see our planet slowly receding in the distance now. And as we travel farther and farther out away from our planet, we'll soon be crossing tremendous distances. We'll start off by traveling to our nearest neighbor, the Moon, which is where that was the farthest astronauts went about 50 years ago. And let me add in the orbit of the Moon, just so we can see where things are. So let's see, the orbit of the Moon should be coming on right there, and the Moon is at the end of the bright end of this blue circle here. That's the orbit of our satellite, the Moon, which circles around our planet once every month, or every month, as some people like to say. And as we travel to the Moon, we're crossing about 250,000 miles, roughly 240,000 miles. It took the Apollo astronauts who went to the Moon 50 years ago about 3 days to cross this distance, but we can do it in just a few short seconds to come up close to our nearest neighbor in space. This is our nearest companion. The Moon is our natural satellite, about 2,000 miles across, so roughly a quarter of the size of Earth. And this is the side of the moon that we normally see from Earth. This is the side that we're most familiar with. It has these dark patches on its surface called the maria. That's a Latin word which means seas, because early astronomers thought that these dark patches were actually bodies of water. So they called them seas and oceans. And they gave them beautiful individual names like the Sea of Rains, which is this big one right here, the Sea of Serenity, and the Sea of Tranquility off to the side here. But they're not really seas and oceans at all. They're actually large flat plains of dried lava, which bubbled up from below the crust a couple of billion years ago, spread out, cooled, and formed this hard surface where craters have subsequently been formed by the impacts of asteroids and comets over the past several billion years, and we can see a lot of those. Some of these craters are huge, like this one here called Copernicus. This crater is about 60 or 70 miles across, one of the bigger craters that we can see on the moon's surface. But there are lots of others. And the lighter colored areas where there are lots more craters, which we can see down here, this is called, this area is called the Lunar Highlands. And you can see there are craters upon craters, and so many that you almost can't count them all. But in a couple of years, with luck, NASA plans to return to the moon via the Artemis program. We went there with the Apollo program, and now we've got a new program going, or NASA does, that is named after the mythological sister of Apollo, that being Artemis. And in a few years, if all goes well, we ought to be going back to the moon, hopefully to stay and set up a lunar outpost there. And as we travel away from the moon now, we're traveling across great distances. We're going to travel across huge distances that are almost too great to measure by miles. And so astronomers use another measure for these great distances, and that's based on the speed of light. So when we talk about things that are really, really far away, astronomers like to use the speed of light as their measuring stick. So when we talk about the distance from the Earth to the moon, instead of saying 93 million, rather 240,000 miles, astronomers like to say 1.5 light seconds, because it takes a beam of light which travels about 186,000 miles per second, takes that beam of light traveling at that speed roughly 1.5 seconds to go from the Earth to the moon. So 1.5 light seconds is the distance from the Earth to the moon. And as we travel even farther out, we'll encounter distances that are even greater than that. When we go out into the solar system and have a look at where the other planets are, we'll show the orbits of the other worlds, looking at the Earth, which is third from the sun. The sun is coming into view at the lower right there. That's 93 million miles away. And according to astronomers, that's about 8.5 light minutes from Earth. So it takes light traveling 186,000 miles per second, 8.5 minutes to travel from the sun to the Earth. Nearest the sun is the planet Mercury, and then next comes the planet Venus, sometimes called Earth's twin. Beautiful, bright planet in the sky. We on Earth are the third planet from the sun, and fourth comes the red planet Mars. Now, after Mars, there's a big gap, which almost is sort of a boundary between the inner planets and the outer planets. And it's interesting that the inner planets are very different from the outer planets. The inner planets are made mostly of rock, and they're fairly small. They're called the terrestrial planets. And then after the four inner planets comes this area called the asteroid belt, the main belt of asteroids, which contains several 100,000 chunks of rock, metal, and debris that are left over from the formation of our solar system. And they form this huge belt here. It's not as crowded as you might think just from looking at this, because space is really, really big, and the space between the asteroids is enormous. In fact, the spacecraft that we've sent out through the asteroid belt have had difficulty encountering asteroids. They weren't so crowded together that you could just run into one without looking. You had to really target an asteroid. The asteroids are really, really, really far apart. Beyond the asteroids, of course, we have the outer planets, the gaseous giants, starting with the planet Jupiter, and then Saturn, and then beyond Saturn are Uranus and Neptune. Those are the 8 planets in our solar system. And speaking of the spacecraft that we have sent out of the solar system. Let's add those in just to show you where they've gone. These are spacecraft that have been traveling away from Earth since about 1973. This is the Voyager, or rather the Pioneer 10 spacecraft. It was launched in about 1973, and then its counterpart, Pioneer 11, was launched in the opposite direction, going off in this direction. And then we have the two Voyager spacecraft. Voyager 1, which is the most distant of our spacecraft, going off in this direction to the upper right, and then Voyager 2, which took a turn downward after it passed Neptune. And then there's the New Horizons spacecraft, which has the shortest path. It went past the little world Pluto not too long ago, and is looking at a couple of other objects out there in this particular region known as the Kuiper Belt. Now, the other spacecraft, Pioneers 10 and 11, Voyagers 1 and 2, they've passed beyond the Kuiper Belt, but New Horizons is still there. And so it's in all of this. It's in this huge mess of rocky debris and rubble. These are short period comets and mini planets, dwarf planets, other members of our solar system, not big enough to be called planets, but they're still substantial. And there are lots and lots and lots of them. There's even another area beyond this called the Oort cloud, which contains long period comets, which is so far out, it's about halfway to the next nearest star. But those are the objects in the Kuiper Belt, also known as the zone of trans-Neptunian objects, and we'll leave them behind and leave our solar system far behind as we enter interstellar space. As we do, traveling between the space between the stars, now we're changing our perspective so that the familiar constellations that we might see seem to change their shapes because we're changing our position relative to those individual stars. Here, for example, is the Southern Cross, generally seen from the southern hemisphere, but as we travel farther and farther out into space, eventually you'll see that configuration of stars lose its familiar shape. The nearest star to us is this one here called Alpha Centauri. It's actually a system of 3 stars located about 4 1/3 light years away. So at the speed of light, it would take a beam of light or a radio signal 4 1/3 years to travel from the sun to Alpha Centauri. And we're going to encounter stars that are even farther away than that. Remember, Alpha Centauri is just the nearest star to the sun. So all the other stars that we see in the sky are a lot farther away than that. And now we're traveling between the stars. Now we've lost the shape of the Southern Cross in the sky, and we're traveling farther and farther out into space. And we're going to encounter our most distant artifact in space, the most distant evidence of humanity, and that is our radio signals, the expanding bubble of our radio signals extending out into space. We've been radiating radio signals out into space from Earth for about the past 90 years or so. And so this is as far as those radio signals have traveled, about 90 light years in radius. So this sphere is about 180 light years across. And notice that this does encompass a number of stars. So if there are any stars within the radiosphere where there might be planets orbiting around them with technologies that enable them to detect radio signals from Earth, they might be hearing our radio signals now. We don't know what they're listening to, but they might be able to listen to our early radio broadcasts. If there's anybody on a planet orbiting a star outside the radiosphere, more than 90 light years away, they haven't heard our radio signals yet, so they wouldn't even know of our existence. So that is the farthest that any artifact from Earth has traveled into space, our radio signals, 90 light years away. Now, as we travel even farther out into space, I'm going to leave the radiosphere on so we can see where we are within our local island universe of stars, within our Milky Way galaxy. Up until about 100 years ago, astronomers thought there was only one galaxy in the entire universe, the Milky Way. And then an astronomer named Edwin Hubble showed that there are other galaxies way outside the Milky Way. And in fact, that those galaxies are moving farther and farther away from each other. Not only did he show us that the universe is bigger than astronomers had thought, but it's getting even bigger still. And look where we are at the center of the radiosphere. Within the Milky Way galaxy, we are nowhere near the center of the galaxy, near that bright hub at the very center. We're off about 2/3 of the way out. So we're not at the center of the Milky Way, where that bright cluster of stars is located. We're out on the fringe, on the edge of one of the spiral arms. The Milky Way is very flat, as you can see. It is just a thin disk of hundreds of billions of stars, measuring about 100,000 light years across. So a beam of light would take about 100,000 years to cross all the way across the diameter of our Milky Way, from one edge all the way across to the other. But that's about average for galaxies. And the Milky Way is just one member of a cluster of galaxies called the local group, which is a cluster of about 80 or so galaxies that includes another large spiral galaxy called the Andromeda Galaxy, and a few others called the Large and Small Magellanic Clouds, the Triangulum Galaxy, and a number of others. And that is our local family of galaxies, a small cluster. And everything you see here, now that we're outside the Milky Way, all the colored dots that you see on your screen, they're not stars. They're actually the locations of distant galaxies, whole galaxies consisting of hundreds of billions of stars. And you can see how galaxies can be clustered together into huge groups, superclusters they're called. Our local group is a small cluster, but superclusters can contain thousands of galaxies. And we'll see more and more of these, and we can see how they're distributed in the universe. This is all based on actual data, of course. Now, scientists have been surveying galaxies and measuring their distances and locations, and this is all based on the actual information that they have collected over the past several decades. And as we travel even farther out, away from the Milky Way, away from our local group, we can see more clusters of galaxies passing by, and you can start to see what looks like a sort of texture to the universe. If you travel far enough out, you can start to see how galaxies are connected in tendrils and wisps and filaments, and separated by large voids or empty spaces. And if you travel farther out, our model of the universe thus far, based on all the data we've collected, based on all the galaxies we've been able to survey, our model of the universe looks something like this, like two huge cones stretching off in opposite directions with a big empty space in between, almost like a giant butterfly or a bow tie or an hourglass almost. Is this really the shape of the universe? Well, actually, no, it's not. This is just the shape of our current model, and the big empty space you see between the two cones is not empty space. It's actually a part of the universe that we haven't been able to survey very well because we can't see it very well. There's something blocking our view, and what's blocking our view is the plane, the disk of our own Milky Way galaxy. Remember, the Milky Way is a thin, flat disk of hundreds of billions of stars, and it lies along this empty space between the cones. And so the dust and gas in the plane of our Milky Way is blocking our view of the more distant galaxies that are way out here. As our technologies and techniques get better, we'll eventually be able to see more of those galaxies in those directions and even out the distribution of galaxies in the universe, and make our map a little more consistent with what's really out there. So no, this is not the real shape of the universe, but it's just part of it. And it tells us that our survey of the universe is not yet complete. Okay, so as we travel even farther back, we're going to come to some of the most distant objects ever detected, and those are what are called quasars. These were very, very bright objects seen from immense distances of about 10 billion light years away. So the light of these objects took in the neighborhood of 10 billion years to reach us, and these are believed to be the most distant objects that we've been able to observe. These are believed to be the cores, the centers of very young newborn galaxies powered by supermassive black holes, which are so energetic they can be seen brightly even across 10 billion light years. Now, the farthest that we've been able to see anything, the edge of what's called the visible universe, is marked by what's called the cosmic microwave background. This is a faint background that comes from all directions, a faint radiation coming from all directions, permeating the entire universe. And this is believed to be the first light that can be detected. Uh, about 13.8 billion years ago, according to astronomers' calculations, the universe was so dense, so hot, so compact and opaque that light couldn't even travel from one place to another. But then suddenly the universe changed. It suddenly became very cool, very rarefied, very transparent, and light was able to travel from one place to another. It took about 300,000 years or so for that to happen. And so this faint background radiation that we're seeing way in the background here, that mottled color, is that first light that was able to travel 300 or so thousand years after the expansion of the universe began. The galaxies continued expanding to the state where we observe them today, and the name that astronomers gave to that point where the galaxies began to expand from each other is known as the Big Bang. It's not the perfect name. It's not the best name for that at all, because that doesn't really describe what happened. It wasn't just something really little that suddenly blew up and bang, all of a sudden there's the universe. There was a change in the phase, in the state of the universe, from very hot, very dense, very opaque, to very thin, very cool, very rarefied. And that faint radiation, the first light that was able to travel from one place to another, is the farthest thing that can be detected by today's instruments. And that being the most distant thing we can detect, we have no place further to go except back in toward the center of our model. And as we do, it may occur to you that it looks like we have placed ourselves at the center of our model, at the center of our universe. Are we really at the center of the universe? Does everything revolve around us? I know some people who would like to think so. But no, this is not the real shape of the universe. It's just a result of the fact that we're the ones who made this model. We're the ones who mapped out the universe around us based on our perspective. If we look around us, we'll see the rest of the universe all the way around, and it'll seem as if we're at the center, but we're really not. If there was somebody in some other part of the universe making their own map of the cosmos, their map would look similar, and it would seem to place them at the very center of it. But as we travel farther back in through the many galaxies that we see, we've seen I don't know how many galaxies there are in the universe. Some astronomers say a good ballpark estimate is several hundred billion, like the number of stars in the Milky Way itself. And with that many stars, that many galaxies, are there other worlds like our own? Are there other solar systems like our own? I mentioned the possibility of there being planets orbiting other stars in the universe. Are there really other worlds that we have found in our universe? Well, since 1995, astronomers have been finding other planets outside our solar system. These are called extrasolar planets, or exoplanets for short. And we're zeroing in on our radiosphere, which at the very center of that is our own solar system. But around it, let me add in the locations of the exoplanets that we know of so far. Now, since 1995, astronomers have been able to detect about 5,000 other planets orbiting distant stars. More than 5,000, actually, 5,000 places where life might take hold far beyond our own solar system. Now, around any of those worlds, could there be, around any of those stars, could there be planets orbiting that conditions might exist to support life? We don't know yet. It takes a lot of very, very special things for a planet to be able to host life. The planet has to be the right kind of planet. We think it needs to be a solid planet like Earth. It has to be a terrestrial world. It has to orbit the right kind of star that doesn't give off too much dangerous radiation. It has to orbit at just the right distance from its star, so it's neither too hot nor too cold. And there are a number of other conditions that have to take place on the planet itself so that it can provide the right kind of nutrients to support life on its surface. It's got to have the right kind of climate. And so there are lots and lots of conditions that must be met in order for life to exist and evolve on the surface of any world, as far as we know. And so far, there is only one world that we know of that fits the bill, and that is our own planet, the third planet from the sun, our own planet Earth. It's the one planet that does have a solid surface. It orbits just the right distance from its star so that it's neither too hot nor too cold. It has oxygen in its atmosphere. It's got the right kind of atmosphere. It's got the right kind of nutrients in its surface to be able to support the kind of life that we find on its surface. It's got liquid water, and that is one of the most important things that we think is necessary for life. And so, that being the case, our planet Earth is the only place that we know of so far where life can exist. And so, in all of our travels through the universe, traveling through the clusters of galaxies and superclusters that we see, we find that there is very true, these words, there is no place like home. And our planet Earth is a very special, fragile place that we need to take good care of. And so let's continue to do our best to do exactly that. And with that, as we return to our home planet, welcome back to the planet Earth. Welcome back home. And thank you very much for joining us on our tour of the universe. Join us every Wednesday at 4:30 p.m. Pacific time. And we hope that we'll see you next time for another tour of the universe. Thank you very much.